So our next chapter is about quadratic functions, and our first section is on modeling data with quadratic functions. So chapter 5, section 1, here we go. Quadratic function is a function that can be written in the standard form. F of x is ax squared plus bx plus c. Now, in order for it to be a quadratic function, it must have a quadratic term. The quadratic term is the one with the square. Now, it may have a linear term, and it may have a constant term, but to be a quadratic function, it must have a quadratic term. Now, hint, a not equal to 0 is the same way of saying that it has to have one. It gives every quadratic function a quadratic term, but not necessarily either of the other two. So, ax squared plus bx plus c. So, let's take a look at some functions. Question. Are these linear or quadratic? Linear means they don't have a squared term, and the quadratic means they do. And I'm going to try to keep my writing to something minimal. Okay, so first we need to simplify. So this becomes f of x is equal to x squared minus x squared. It goes away, so we just have 5x. Ask yourself, does it have a squared term? The answer is no, no squared term. Therefore, it's linear. That's how it works. Look at the next one. Well, this thing tells me I need to FOIL, so f of x is equal to 3x squared minus x minus 15x plus 5, or 3x squared minus 16x plus 5. Look it over really good. Look at that. I have a squared term. So since it has a squared term, it is quadratic. All right, I'll give you a second here. You look at C. What do you think is going to happen? We look at C, and we see that f of x is x squared plus 3x. It has a squared term, so it's quadratic. Okay. And we look at the next one. We simplify. 3x squared minus 6x minus 3x squared plus 6. Well, 3x squared minus 3x squared, they go away. So I get negative 6x plus 6. No squared term, so this one is linear. Okay, that's how it works. So we multiply it out, simplify it first, then we decide. If it has a squared term, it's quadratic. If it doesn't have a squared term, it's linear. But always simplify first. Okay, that may mean distributing, that may mean just collecting like terms. It can mean lots of things, but always simplify first. Okay, so far so good. All right, so the graph of a quadratic function is a parabola. The axis of symmetry is the line that divides the parabola into two parts that are mirror images. We can also call it, it's kind of like the folding line when you used to cut out paper hearts in grade school. It's the folding line. It's the line that you folded it on, and then both halves look the same. So the vertex of the parabola is where the parabola itself, see this guy right here is the parabola, when the parabola itself meets the axis of symmetry. In our case, the axis of symmetry is right here. Okay, the y value of the vertex of the parabola represents the maximum or the minimum. Okay, we'll talk about those in a second, but let's take about that. The vertex, it comes from the vertex. Okay, so we take a look at this first one. And we can see that the axis of symmetry is right here. And any vertical line has the equation x equals. What does x equal in this case? Well, x equals 0. So the axis of symmetry is x equals 0. Now the vertex is where the parabola itself meets that line. So when x is 0, what is y? Well, it's also 0 in this case. So our vertex is 0, 0. Okay, we always write the vertex. The x part of the vertex is always the axis of symmetry, and we always write it like this. So take a look at the second one here. You can see the vertex is right there. It also is at 0, 0. So if we use that, x equals 0 is my axis of symmetry. Two different parabolas. This one opens up. This one has a minimum. Why? Because it has a point that is the lowest point. This one has a maximum because it has the tallest point or the highest point on the parabola. These two terms, maximum and minimum, play a very, very, very key role in the things we're going to do in this chapter. So minimum is the lowest point, maximum is the highest point. A parabola can only have one or the other. It will never have both. Okay, here's the graph of the parabola. It says it's y equals, I'm going to circle this, x squared minus 6x plus 11. It says identify the vertex, the axis of symmetry, and the points corresponding to P and Q. All right, so first thing, we have the axis of symmetry and the vertex. So here's my axis of symmetry. It's right here. I know that because it's the middle of it. And here's my vertex. So I have to count over. It's 1, 2, 3. So x equals 3 is my vertex, or my axis of symmetry. If x is 3, plug it into the equation. Then what is y? Sorry, if x is 3, y is 3 squared minus 6 times 3 plus 11, or 9 minus 18 plus 11. 9 minus 18 is negative 9 plus 11 is 2. So my vertex is 3, 2. Okay, my vertex. So far, so good. Okay, if point Q is right here, then opposite point Q, on the opposite side of the axis of symmetry, we have what we call Q prime, or Q's partner, or corresponding point. It's the same distance from the axis of symmetry as the original point. So if my original Q is 4, 3, okay, and my axis of symmetry is x equals 3, it's 1 unit beyond. I want to go 1 unit back, so Q prime is going to be 2, 3. Kind of tricky there. All right, let's look at point P. Point P is up here. Okay, he's at the point 1, 6, and P is 2 boxes away from the axis of symmetry. So if I go 2 boxes to the other side of the axis of symmetry, I'm now at 5, 6. Notice the y values stayed the same. The x values are the ones that changed. Question, does this parabola have a maximum or a minimum at its vertex? Well, think about it. If it opens up and it holds water like a cup, then it has a minimum. If it opens up, so it holds water like a cup, then it's a minimum. So far, so good. Let's look at another one. Here's a second parabola. This one's a little harder to see. Let me see if I can zoom in a little for you. Maybe a little more. There we go. I know I got a lot of stray marks here, but it'll work. Okay, first I have to find the axis of symmetry and the vertex. So I look at the parabola. The lowest point is this point right there. Can I name that point? I sure can. If this is 2 and that is 4, then this must be 3. So my vertex is 3, -2 using the scale I see on the grid. Okay, so here's my axis of symmetry. Let me put it in there very, very, very carefully. Here it is. Okay, kind of dotting it in there. Okay. So if I have a point that's 2.5, or if I have a point that's 1, 2, 3 boxes to the left, then I also get a point 3 boxes to the right, the partner points. So take a look up here. This point is 1, 2, 3, 4, 5, 6 boxes to the left. So 1, 2, 3, 4, 5, oh, look at that, 6 boxes to the right is another point that matches up. Pick those because they're easy to see. Okay, so we have our vertex. Can you tell me if that vertex represents a maximum or a minimum? I'm hoping you're saying minimum. Again, it's at the bottom. It's at the lowest possible point. So I'm hoping you see that that is a minimum. Sorry, I didn't realize that was off the screen. So, okay, we found the vertex. We found, oh, the axis of symmetry is the x part of that. So x equals 3 is my axis of symmetry. All right, last problem. Okay, take a look. I should have done one that opens down. Sorry, I guess I should do that. Let's take a look. Again, I have a minimum because it's opening up like a cup. Here's my vertex, so I find it. It's 3, 4. So that tells me my axis of symmetry is whatever that is, so it's x equals 3. Remember, this is x, y, so whatever x is, that's the axis of symmetry. Here it is. Okay, that's how it works. Okay, so if I have a point that's right here, I find where the axis of symmetry is, and that means I have to have a point right there because they have to be the same distance away. Now we use that point itself when we graph. Right now we're not graphing right now, we're just looking at a graph. We can find the vertex, we can find the axis of symmetry, and we could find some partner points if we wanted to. For example, we could name these 2 points. This is the point 1, 8. Okay, and it's 1, 2, 3, 4 boxes away. So 1 to 4 boxes away is 5. 4 more boxes would be 9, 8. That doesn't look right. 4 boxes, sorry. This is 1. Here's 2, here's 3, here's 4. This is 5, 8. I didn't look at the scale. That was my fault. I should have looked at the scale. This is the point 5, 8, not 9, 8. Yeah, silly me. What was I thinking? Okay, that is a really quick video on how to model quadratic functions with using graphs. We're going to talk about this a little bit, and we'll see what we can do for you in class on the next time we meet. See you then.